Hello everyone. So in this pre-lecture tutorial, now that we understand more or less how atomic energy levels and atomic orbitals work, we're going to start to discuss how it is that electrons fill into the atomic structure. And so in order to understand how that works, we need to have a couple of rules in mind. We still have to keep track of the Pauli exclusion principle, all right? And so we'll discuss that a little bit later. But then we also must be aware of sort of the guiding principle for how electrons fill into an atom structure. And that guiding principle is called the Aufbau principle. And all that really means is that electrons fill in to the structure of an atom from the lowest energy level to the highest energy level. And so the next thing that we have to keep in mind is understanding the relative energies of all of these different energy levels and all of these different orbitals. And so that isn't as easy as it might seem. I think that now that we understand how orbitals work, you might be tempted to think, oh, well, I have my 1s orbital, my 2s, my 2p, my 3s, my 3p, my 3d, and then 4s, and 4p, and 4d, and 4f, and so on. And so we assume that the energies just go in order of the orbitals as we've come to learn about them. But the fact of the matter is it isn't quite that simple. All right, the following energy level diagram shows that the lowest energy level is indeed the 1s. That's the lowest energy orbital. Then the 2s fills, but then the 2p. 3s, 3p, but notice that the 4s orbital actually fills before the 3d. Then the 4p fills, but then notice that before we get to the 4d, the 5s fills before the 4d, and so on. And so what starts to happen is we start to get a mixing of the different orbitals in their energy levels in terms of following them from their lowest energy to their highest energy. And so that can make it a challenge to remember how it is that these electrons fill in to the atomic orbitals properly. Now, luckily there is a chart that I often recommend that makes it easier. I call this the pyramid diagram. And basically what you do is you actually write out the orbitals that we've learned about so far. And so you actually start to make a list much like this that I started to make earlier. And you do it for all of the orbitals that exist through the 7p orbital, because remember we mentioned in class last week that basically we only really get to the 7th energy level in terms of the elements that exist currently in the periodic table. And so we could in theory keep writing out all of these different orbitals, but we don't really see any electrons past the 7p orbital. And so we stop listing out the orbitals that we know there. So basically in the first energy level we just have the 1s, in the second we have 2s and 2p, in the third we have 3s, 3p, 3d, and so on. And the way that we remember the way that they fill is once we actually have our list of orbitals written out, we're going to actually draw diagonal arrows from the upper right to the lower left through the different orbital designations. So that means that when I actually fill orbitals with electrons in an atomic structure, just like the picture shows up above, the 1s will fill first, then the 2s, then the 2p, then the 3s, then the 3p, but then the 4s fills next. Then, after the 4s, I have to go to the next diagonal arrow, so the 3d will actually fill before the 4p does, and so on. And so, using this pyramid diagram can be extremely useful in terms of figuring out the order in which electrons fill into the atomic structure. And so, let's actually apply this tool to an example of an element's atomic structure and see how it's used. And so suppose I was asked to describe the electronic structure of a sulfur atom. Okay, I can actually do this description one of two ways. One is called the orbital diagram. And then there's something else that we call an electron configuration notation. And so if I'm going to fill electrons into either of these, then I'm going to need to know how many electrons exist in the sulfur atom. So if I consult the periodic table, basically sulfur has atomic number 16. So that means it has 16 protons, but it also has 16 electrons. Okay, now basically I need to then figure out, okay, what orbitals fill in what order. And so for this orbital diagram, I'm actually going to make it similar to this diagram that I actually showed you in the previous slide. I'm going to draw a line that represents my 1s orbital. Now, after the 1s orbital, I will then have my 2s, my 2p, 3s, 3p, and so on. Now, remember that when I consider orbitals, remember that each orbital can handle a maximum of 2 electrons per orbital. So that means this 1s orbital can actually have 2 electrons within it, but recall that by the Pauli exclusion principle, that means that these electrons must be of opposite spin. So we tend to show these electrons as arrows. And so the 1s orbital should have 2 electrons, one being spin up, the next being spin down. So I'm going to go and I'm going to check my pyramid diagram. After I fill the 1s, the 2s should fill. And so I'm going to draw a line for my 2s orbital. Okay, now again, a 2s, just like the 1s, can fill 2 electrons provided they are in opposite spins. And so far, what that's given me, it's given me the opportunity to fill in 4 of these 16 electrons in sulfur's electronic structure. Now, that means I still have 12 electrons to go. And so what I'm going to do next is I'm going to go and fill my 2p orbital, since that is the orbital that occurs next, or the sublevel that occurs next. So these 3 lines represent each of the orbitals in the 2p sublevel. Now, again, each of them can hold 2 electrons, but there's a rule called Hund's rule that says that basically for electrons occupying the same sublevel with multiple orbitals, then what's going to happen is I'm going to fill each orbital with 1 electron before starting to pair them up. So here's what I mean by that. We know that the 2p sublevel can accommodate a maximum of 6 electrons. But I'm not going to start off pairing them up like this first. What I'm going to do is add 1 electron to each. So that's 1, 2, 3. But then, since I still need 3 more electrons in this 2p sublevel, then I'm going to start pairing them up. 4, 5, and 6. So I still need to place 6 more electrons, because basically I've already accommodated 10 in my electron structure. Now, my next orbital should be my 3s orbital. So I'm going to draw a single line representing the single orientation of an s orbital and put 2 more electrons there. So now I have to accommodate 4 electrons more. Since the 3s is filled, now I have to move to my 3p orbital. So I'm going to go and put in 3 lines, 1 for each orientation of the p orbitals in the 3rd energy level, and now I'm going to add in 4 electrons. But again, recall Hund's rule. basically I'm going to need to go and add in 1 electron apiece into each of the orientations of the p sublevel, but I still need to add 1 more electron, so I'm going to pair one of them up. And that would be the proper orbital diagram for the electronic structure of the sulfur atom. Now, as it turns out, I can also take a more condensed form of this. I can go and actually create a string of orbital designations and go and put in the number of electrons in each orbital as a superscript above that sublevel designation. So for example, I have this electron configuration, right? This electron arrangement in sulfur. I have the 1s sublevel with 2 electrons in it. I have the 2s sublevel also with 2 electrons in it. The 2p has 6 electrons in it. But the 3s has 2, and the 3p has 4. So this is considered to be the electron configuration for a sulfur atom. Now, I could even abbreviate this further, because if I take a look in the periodic table, basically the noble gas that precedes sulfur is neon. So if I go and include neon in square brackets, that represents 1s2, 2s2, 2p6, because that would be neon's electron configuration. Then all I have to do to finish out what we call this abbreviated electron configuration notation is to just write the remainder of the configuration. That would be 3s2, 3p4 for sulfur. And so this would be an abbreviated way to show the electron configuration for sulfur, which in turn is an abbreviated form of the orbital diagram that shows us where the electrons actually reside within the energy levels within a sulfur atom. So I know that this is a new concept. I know it's going to require some practice. So go ahead and work on the follow-up assignment that we have related to this particular subject area, and make sure that if you have any questions, you email. Obviously, we'll also discuss this further in class. All right? Have a good night.